So right now we have both. Both of these are recursive solutions to towers of Hanoi. And I want to take a moment to really look at these and see if we can notice any patterns between the two, because we'd like to try and get this into an iterative solution. So I'm just going to scroll down this slowly, and feel free to pause whenever you want just to check this out, because I want to see if you can figure out any patterns before we get into it together. So you may have noticed some things. In particular, between these two, one is always going to be moving in an alternative fashion, where we always move one, and then we're going to move a bigger disk. We're always going to be moving one, then a bigger disk. And this also works the same on even tower disks. So 1, 2, 2, move 1. Yeah, move 1 from here to here. Then move 3. Then move 1. Then move 2. So on and so forth. You may notice as well that as soon as we move 1, we're kind of locked into our next move that we can do, because we only have 2 towers that we can really choose from. So once we get to this point, our next move is almost forced for us. So we just moved 1 right here. So our only 2 towers that we can choose from are this one and this one. Obviously this one doesn't have anything, so we're going to be moving from here to here. Let's give another example. Let's see. So we just moved 1 again. Yeah, so now we're locked into these 2 towers. So I mean, obviously the 2 has to go on top of the 3. So as soon as we move our 1, we're forced to take another move with our other tower. So we can continue to make observations like this, and eventually we'll get to a very, very cool algorithm. So let me wave my hands a bit and let me show you what this algorithm is going to look like. So we are going to set up our 3 towers again. So again, let's call them A, B, and C. And let me just give this to you. So, and I want to say, let's observe only 2 towers at a time. Let's observe first. Let's observe A and C. Then let's observe A and B. Second. And third, let's observe B and C. So again, you don't have to understand how we got to this. I just want you to understand how to implement it, but what the algorithm is, so you can implement it for your project. So this is only going to work for odd number of disks. And what exactly is the algorithm? Every move that we make, we're going to follow this pattern. So on the first iteration, on the first move, we're going to look between A and C. We're going to say, all right, there can only be one legal move here. Which one is that legal move? And we're going to make it. So in this case, it's just going to be move this one here. So let's do that. Just make a move here, erase this. So this one's going to be that one. Again, let's make another erasure. We're going to check out this one between A and B. We only can move this one that I just erased to B. So let's place that there. And now we're going to look between C and B. So now C is smaller than b, so we're going to move the smaller one to b. And I think you start to get the idea. This is now our next iteration. So we're just going to get rid of this. And then we're just going to move it right here. And I'll let you do this one for the rest of yourself. But this is going to be the algorithm for all odd number disks and then the next algorithm is going to be for all even. So we're looking at, again, A, B, and C. And again, you don't have to understand how we got to this point. Just understand the algorithm so that you can implement it for yourself. So this one is just going to be 1. Check between these two towers. Then check between these two. And then finally, check between these two. So again, what do I mean by check? So when I say check between two towers, I'm saying check between these two towers, look for the smaller ring on these two towers, and whichever is smaller, take that ring and move it to the other tower. So between these two, if I were to say check these two, this would be the smaller ring. So we just take this one and just move it to the next other tower. And again, for this algorithm, this is going to be for all even number of disks. So when it comes to the implementation of this, how are we going to do this? I mean, we've already seen with the recursive solution that we're going to be using vectors. So when it comes down to it, the easiest solution would be to make some kind of function called make legal move. That just takes in two parameters, tower 1 and tower 2. So this is going to be just indexes to those towers in our representation of this entire tower system. And we say, all right, we have the both indexes for the tower that we want to observe. So maybe A and B if we're on our first iteration, or A and C on our second. And we want to say, all right, check which one is the smaller. For whichever one that's smaller, just grab that ring and put it on this one. And if for some reason we were on a tower that they were empty, we would just say, all right, we'll just take that ring and just put it to the empty tower. And when should this algorithm end? Well, as soon as the tower that we're looking to get to has all 3 disks. So in this case, we'd probably use something like vector.size. So once the size of this tower is equal to the number of disks, then we can say we are done.